Imagine you're throwing a basketball toward a hoop. Have you ever noticed that the ball follows a curved path through the air? This isn't just any curve, it's a very special mathematical shape called a parabola. Watch as the ball travels through the air, following this curved trajectory. This path represents what mathematicians call a quadratic function, and understanding its properties will help you solve many real-world problems. Today we're going to explore quadratic equations and two of their most important features, the vertex form and the axis of symmetry. These concepts are fundamental to understanding parabolas and will appear throughout algebra, physics, and engineering. A quadratic equation is any equation that can be written in the standard form, ax squared plus bx plus c equals 0, where a, b, and c are constants, and most importantly, a cannot equal 0. When we graph a quadratic equation, we get a U-shaped curve called a parabola. This curve has several important characteristics that we need to understand. The most important point on any parabola is called the vertex. This is the turning point where the parabola changes direction. For a parabola that opens upward like this one, the vertex represents the minimum point. The second key feature is the axis of symmetry. This is an imaginary vertical line that passes through the vertex and divides the parabola into two identical halves. If you could fold the parabola along this line, both sides would match perfectly. Notice how the parabola is perfectly symmetrical about this vertical line. Every point on the left side has a corresponding point on the right side at the same distance from the axis of symmetry. Understanding these concepts is crucial because they help us analyze quadratic functions quickly and solve real-world problems involving projectile motion, optimization, and many other applications. In the upcoming sections of this video, we'll learn the specific formulas for finding the vertex and axis of symmetry, work through detailed examples, and see how these concepts apply to practical situations. By the end, you'll be confident in identifying and using these key features of any quadratic equation. Now that we understand what vertex form is, we need to learn how to find the vertex when we start with a quadratic equation in standard form. This is where the vertex formula becomes essential. The vertex formula gives us a direct way to find the x-coordinate of the vertex. This formula is h equals negative b divided by 2a. Let me break down what each part of this formula means. The letter h represents the x-coordinate of the vertex. The letters a and b are the coefficients from our standard form equation. Once we find h, we can find the y-coordinate of the vertex, which we call k, by substituting h back into the original equation. So k equals f of h. Now I want to show you visually how the coefficients a and b affect where the vertex is located. We'll start with a simple parabola and see what happens when we change these values. First, let's look at the equation y equals x squared. Here, a equals 1 and b equals 0. Using our vertex formula, h equals negative 0 divided by 2 times 1, which gives us h equals 0. Now let's change the equation to y equals x squared plus 4x. Here, a is still 1, but b is now 4. Using the vertex formula, h equals negative 4 divided by 2 times 1, which equals negative 2. Notice how changing the b coefficient moved the vertex horizontally. When b was 0, the vertex was at x equals 0. When b became 4, the vertex moved to x equals negative 2. Now let's see what happens when we change the a coefficient. Consider y equals 2x squared plus 4x. Here a equals 2 and b equals 4. The vertex formula gives us h equals negative 4 divided by 2 times 2, which equals negative 1. This demonstrates a key insight. Both the a and b coefficients affect the horizontal position of the vertex through the formula h equals negative b divided by 2a. The vertex formula captures this relationship perfectly. Now that we understand the vertex formula, we need to explore a closely related concept, the axis of symmetry. The axis of symmetry is a fundamental property of every parabola that helps us understand its structure and behavior. The axis of symmetry is a vertical line that passes through the vertex of the parabola. Think of it as an invisible line that if you folded the parabola along it, both sides would match perfectly. The formula for the axis of symmetry is equals negative b divided by 2a. Notice that this is exactly the same as the x-coordinate of the vertex that we learned about earlier. Now I'll show you visually what this means. Here's a parabola with the equation y equals x squared minus 4x plus 3. Using our formula, the axis of symmetry is x equals negative 4 divided by 2 times 1, which gives us x equals 2. Now I'll draw the parabola and show you exactly where this axis of symmetry appears. Watch as the parabola forms, and then I'll add the vertical line at x equals 2. Here's the amazing property of the axis of symmetry. It divides the parabola into two perfect mirror images. If I pick any point on one side of the line, there's an identical point at the same distance on the other side. Let me show you another example to reinforce this concept. Consider the parabola y equals negative 2x squared plus 8x minus 6. Here, a equals negative 2 and b equals 8. Even though this parabola opens downward and has different coefficients, the axis of symmetry is still at x equals 2. This shows that the formula works for any quadratic equation, regardless of the shape or orientation of the parabola. Let me show you one more example with a different axis of symmetry. For the equation y equals x squared plus 6x plus 5, we have a equals 1 and b equals 6. The axis of symmetry is x equals negative 6 divided by 2 times 1, which gives us x equals negative 3. Remember, the key insight is that the axis of symmetry formula x equals negative b over 2a gives you the exact x-coordinate where the parabola is perfectly balanced. This vertical line always passes through the vertex and divides the parabola into two identical halves. Now we're ready to work through our first example. We'll find the vertex and axis of symmetry for a quadratic equation step by step. Here's our quadratic equation in standard form. We have y equals x squared plus 4x plus 3. Our goal is to find two things: the vertex coordinates and the equation of the axis of symmetry. Let me show you what we need to find. First, we need to identify the coefficients a, b, and c from our standard form equation. Remember, standard form is at x squared plus bx plus c. Looking at our equation y equals x squared plus 4x plus 3, we can identify a equals 1, b equals 4, and c equals 3. Now we'll use the vertex formula to find the x-coordinate of the vertex. The formula is h equals negative b divided by 2a. Let's substitute our values. We have h equals negative 4 divided by 2 times 1. Simplifying this, we get h equals negative 4 divided by 2, which equals negative 2. Now we need to find the y-coordinate of the vertex by substituting h equals negative 2 back into our original equation. Let's calculate this step by step. First, negative 2 squared equals 4. Next, 4 times negative 2 equals negative 8. Finally, 4 minus 8 plus 3 equals negative 1. Perfect. Now we have both coordinates. The vertex is at the point negative 2, negative 1. The axis of symmetry is a vertical line that passes through the vertex. Its equation is x equals the x-coordinate of the vertex. Now let's visualize this on a graph to see how the vertex and axis of symmetry look on the actual parabola. Here's our parabola for y equals x squared plus 4x plus 3. Notice how it opens upward since our coefficient a is positive. Here's our vertex at the point negative 2, negative 1. This is the lowest point of the parabola since it opens upward. And here's the axis of symmetry, the vertical line x equals negative 2. Notice how it passes through the vertex and divides the parabola into two mirror image halves. This completes our first example. We successfully found that the vertex is at negative 2, negative 1, and the axis of symmetry is the line x equals negative 2. The key steps were identifying our coefficients, applying the vertex formula, and then visualizing the results on the graph. Now we'll work through a more challenging example that involves negative coefficients. This is where many students make sign errors, so we'll be extra careful with our calculations. Here's our quadratic equation. Y equals negative 2x squared minus 8x minus 5. Notice that we have negative coefficients, which requires extra attention to signs. First, let's carefully identify our coefficients. The coefficient a equals negative 2. The coefficient b equals negative 8, and the coefficient c equals negative 5. Notice that all three coefficients are negative in this example. Step 2, we'll find the x-coordinate of the vertex using the formula h equals negative b divided by 2a. Now we substitute our values. H equals negative, open parentheses, negative 8, close parentheses, divided by 2 times open parentheses, negative 2, close parentheses. Let's simplify step by step. In the denominator, 2 times negative 2 equals negative 4. So we have h equals negative 8 divided by negative 4. When we have negative 8 divided by negative 4, The negatives cancel out, giving us positive 8 divided by 4, which equals 2. So h equals 2. Now that we have the x-coordinate of the vertex, we need to find the y-coordinate by substituting h back into the original equation. Step 3. To find the y-coordinate, we substitute h equals 2 into our original equation. So k equals negative 2 times 2 squared minus 8 times 2 minus 5. First, 2 squared equals 4 and 8 times 2 equals 16. So we have k equals negative 2 times 4 minus 16 minus 5. Next, negative 2 times 4 equals negative 8. So k equals negative 8 minus 16 minus 5. Finally, negative 8 minus 16 minus 5 equals negative 29. So k equals negative 29. Now we can state the coordinates of the vertex and write the equation of the axis of symmetry. The vertex is located at the point 2, negative 29. The axis of symmetry is the vertical line x equals 2. Now let's visualize this parabola on a coordinate plane. Since our coefficient a is negative 2, the parabola opens downward and the vertex represents the maximum point. Here's our parabola graphed on the coordinate plane. You can see it opens downward because the coefficient a is negative. The vertex at 2, negative 29, is the highest point on the curve, and the dashed line x equals 2 is the axis of symmetry that divides the parabola into two mirror image halves. This example demonstrates how important it is to carefully track negative signs throughout your calculations. The negative coefficient of x squared makes the parabola open downward, and the negative coefficients in our calculations led to a vertex with a negative y-coordinate. Now we'll explore how vertex form applies to real-world scenarios through a projectile motion problem. This type of problem appears frequently in physics and engineering applications. A ball is thrown into the air from a height of 5 feet. Its height at any time t is given by the equation h of t equals negative 16t squared plus 64t plus 5, where h of t is the height in feet and t is the time in seconds. We need to find two things. First, the maximum height of the ball, and second, the time when the ball reaches this maximum height. The key insight is that the maximum height occurs at the vertex of the parabola. Since the coefficient of t squared is negative, the parabola opens downward, making the vertex the highest point. Now let's solve this step by step using the vertex formula we learned earlier. Step 1. We identify the coefficients from our equation. Comparing h of t equals negative 16t squared plus 64t plus 5 to the standard form, we have a equals negative 16, b equals 64, and c equals 5. Step 2. To find the time at maximum height, we use the vertex formula. The t-coordinate of the vertex is given by t equals negative b divided by 2a. Now we substitute our values. T equals negative 64 divided by 2 times negative 16. First, we calculate the denominator. 2 times negative 16 equals negative 32. Negative 64 divided by negative 32 equals positive 2. So the ball reaches its maximum height at t equals 2 seconds. Now that we know when the maximum height occurs, let's find what that maximum height actually is. Step 3. To find the maximum height, we substitute t equals 2 back into our original equation. H of 2 equals negative 16 times 2 squared plus 64 times 2 plus 5. First, we calculate 2 squared equals 4, and 64 times 2 equals 128. Next, negative 16 times 4 equals negative 64. Finally, negative 64 plus 128 plus 5 equals 69. So the maximum height is 69 feet. Now let's visualize this problem with a graph to see the parabolic path of the ball. Here's a graph showing the ball's trajectory over time. The horizontal axis represents time in seconds, and the vertical axis represents height in feet. The parabola shows the path of the ball. Notice how it starts at 5 feet, rises to a maximum, then falls back down. The vertex of the parabola occurs at the point 2, 69, representing our maximum height of 69 feet at time 2 seconds. The dashed line shows the axis of symmetry at t equals 2. This line divides the parabola into two mirror image halves. Watch as the ball follows this parabolic path. It starts at 5 feet, reaches its maximum height of 69 feet at 2 seconds, then continues downward. To summarize our solution, the ball reaches its maximum height of 69 feet at exactly 2 seconds after being thrown. This demonstrates how the vertex formula helps us solve real-world projectile motion problems. In practical terms, this means that if you were throwing a ball with this initial velocity and height, You would know exactly when to expect it to reach its peak and how high it will go. This type of analysis is crucial in sports, engineering, and physics applications. Now that we've worked through several examples, it's crucial to understand the most common mistakes students make when finding the vertex and axis of symmetry. Avoiding these pitfalls will help you solve problems accurately and confidently. The first common mistake is misidentifying the coefficients a, b, and c. Students often forget to include negative signs. For example, in the equation y equals negative 2x squared plus 3x minus 1, the correct values are a equals negative 2, b equals 3, and c equals negative 1. Notice how the negative signs are part of the coefficients themselves. The second major mistake involves the vertex formula itself. Remember that the x-coordinate of the vertex is h equals negative b divided by 2a. The negative sign is crucial and is often forgotten. The third common mistake occurs when substituting the h value back into the original equation to find k. Students often make arithmetic errors or forget to follow the order of operations correctly. One of the best ways to check your work is through visual verification. Always graph your parabola and verify that your calculated vertex and axis of symmetry match what you see on the graph. Remember, practice makes perfect. Work through different types of problems, check your answers visually when possible, and don't rush through the calculations. Take your time with each step, and you'll master finding the vertex and axis of symmetry with confidence. Now that we've explored vertex form and axis of symmetry through multiple examples, it's time to recap the essential concepts you've learned today. There are three fundamental concepts that form the foundation of working with quadratic functions in vertex form. First, the vertex formula. The x-coordinate of any parabola's vertex is found using h equals negative b divided by 2a. This single formula unlocks the turning point of any quadratic function. Second, the axis of symmetry. Notice this uses the exact same formula, x equals negative b divided by 2a. This vertical line passes through the vertex and divides the parabola into two mirror images. Third, the systematic approach to solving problems. Always start by identifying your coefficients a, b, and c. Then calculate h using our formula. Substitute h back to find k. Finally, you have your vertex coordinates and axis of symmetry. To reinforce these concepts visually, observe how these formulas work together on an actual parabola. Here we have the parabola y equals x squared minus 2x plus 3. Using our formulas, the vertex is at coordinates 1, 2, and the axis of symmetry is the vertical line x equals 1. Understanding these concepts is crucial because they form the foundation for analyzing any quadratic function, whether you're graphing parabolas, solving optimization problems, or modeling real-world phenomena. These skills will serve you well beyond this single topic. They're essential for graphing, crucial for optimization problems, and fundamental for success in higher-level mathematics courses. If you found this tutorial helpful, I'd really appreciate your support. Please give this video a thumbs up if it helped you understand vertex form and axis of symmetry. Subscribe to the channel for more step-by-step math tutorials like this one. And don't hesitate to ask questions in the comments section below. Whether you need clarification on today's topic or have suggestions for future videos, I read every comment and try to respond to as many as possible. Speaking of future videos, you won't want to miss what's coming next. In our next tutorial, we'll dive deep into completing the square, the essential technique for converting any quadratic equation from standard form to vertex form. This skill will give you complete mastery over quadratic functions. Thank you for watching, and I'll see you in the next video where we'll continue building your algebra skills step by step.